All right, example 7. So this is a problem where we're also asked to find the center of mass of an object. But this time, instead of a group of particles like the last problem, this is a continuous mass. So we're going to use the integral form of the center of mass equation. So what we have is, as outlined in green here, we have a rod. It has length L and has uniform density throughout. So this is called linear density, and it's the mass per unit length. So like every inch you go, it weighs an ounce. All right, so 1 ounce per inch, or a kilogram per meter, something like that. All right, so for this case, that linear density, we're considering that to be constant, but it doesn't have to be. All right, but in this example, it is. So let's set this up here. We have our rod. Its fixed length is L. X is the distance from the origin to any point along the rod. Dx is the width of the little infinitesimal pieces that we're going to break this rod up into as we. So we're going to think about this rod being made up of, as we do in calculus, think of the rod as being made up of many tiny pieces of length dx. So the mass of each of these infinitesimal pieces is a differential mass, and that's going to equal the mass per unit length times the length. And dx is the length of the little piece that makes it up. And this is mass per length, so that works out to a mass. All right, so let's hit the equation. The center of mass, the x-coordinate of the center of mass, it's 1 over the total mass times the integral of x dm. Now, we just found dm, so we can substitute that in. And this integral is over the whole length of this, so it goes from 0 to L. The x is still there. Now dm is lambda dx, so we put that in for dm. This is dm. Okay, don't want to leave that in there because that'll get confusing. Bring out the lambda and the m because they're both constants. All right, and then we have the integral of x dx, which is x squared over 2, and that's evaluated between 0 and L. 0 is just going to give us a 0 result. So x cm equals lambda L squared over 2m. But we're not done. We have an expression for lambda. We know lambda equals m over L. And so we can substitute that in here. So xcm equals m over L times L squared over 2m. And the square and that L go out. The m and the m goes out. So we end up with L over 2. So the center of mass is right in the middle of the rod, which is not a surprise. But it's a nice check to show that this method works for, and you can trust it for more complicated geometry that you can't tell just by looking at it.